Welcome to Let's Get to the Marks, going through a time of flight mass spectrometry question. You can see the stem of the question here. If you're interested in some more of these, I've gone through the latest one on this link here to this video. That's the latest one by AQA. And at the end of this video, you'll see a couple more videos I've done on time of flight. You might want to work through a whole section. Let's get down. 2.1, describe how the molecules are ionized using electrospray ionization. This is the same for anything that you ionize with electrospray ionization. We're going to use a volatile solvent. We're going to dissolve the sample, the molecules, the compounds into a volatile solvent. Why do we use a volatile solvent? It's not relevant to this question, but the volatile nature of the solvent means that it evaporates quickly after we've added it and before the sample is injected. Now, the second part to this is we inject the sample through a needle whilst passing a high voltage across the nozzle of the needle. And what this does is this creates a positive charge on the compound or the molecule by adding a hydrogen ion or a proton to the molecule. And those are the three marks. So dissolve with a volatile solvent, pass through a high voltage, and a proton's added. Let's zing. 2.2, give the formula of the ion that reaches the detector first in the time of flight mass spectrometer. So if we zing back up, we can see the three different compounds with their molecular formulas, C3H5O2N. What we want to do is work out the mass of each of these because the lightest one is likely to reach the detector first, right? So we've got 36 plus 5 plus 32 plus 14. And then for this next one, we want to do C3H7O3N. So that's going to be 3 times 12 carbons is 36 again. This time we've got 7 hydrogens, so plus 7. This time 3 oxygens, so 3 times 16 is 48, plus 14 for the nitrogen. And then we got C3H7O2NS. So again, we've got 36 for the carbon, 7 for the hydrogen, 32 for the 2 oxygens, and we have 14 for the nitrogen and another 32 for the sulfur atom. Now, if we add these mass numbers all up, we're going to get like, and I might have got this roughly wrong, but roughly, people, we just want to find which one's the lightest. So as long as it's not close, 87 for the top one, and then something like 107, is it for the next one? And then, or 105, and then 121. So the lightest one here is this C3H5O2N that's going to reach the detector first. Let's not forget that it's electrospray ionization and we added a proton. Therefore, the mass will increase to 88. We're not asked about the mass here, but there are questions which ask you that. So the formula is going to be C3H5O2N plus. The plus represents the proton. Some people don't like to just write the plus. They want to write H plus. That's totally fine. H plus or plus, they're both protons, so they're equal to each other. So those are the correct formulas. Okay, 2.3, a sample of germanium is analyzed in TOF, time of flight mass spectrometer, using electron impact ionization, given equation, including state symbols for the process that occurs during the ionization of a germanium atom. Okay, so what's the symbol for germanium? It's capital G with lowercase e. It's going to be in the gaseous phase because we must vaporize them when we're going to ionize them. It's hit by a beam of electrons from an electron gun that adds an electron that knocks an electron off of the germanium. It rams into it and smashes an electron from the outer shell. So we don't just get the electron from the electron gun, but we get the electron that's knocked off as well. So we've got 2 electrons on the right hand side. Don't forget the positive sign for the germanium. It's now an ion, and the gaseous symbols are important too. Right, moving on to the final part, we're looking at 2.4. In the time of flight mass spectrometer, a germanium ion reaches the detector in 4.654 times 10 to the minus 6 seconds. So we've got the time there. The kinetic energy of this ion is 2.438 times 10 to the minus 15 joules. The length of the flight tube is 96 centimeters, but yeah, so we've got distance and time, and that should make us think of speed equals distance over time. You always need that equation in the time of flight. I've never seen one without where you don't need speed equals distance over time or velocity equals distance over time. And they will always give you kinetic energy is equal to half mass times velocity squared. So let's start with the distance. We've got 96 centimeters. We want to divide by 100 to get 0.96 meters. We want to divide that by the time, which is 4.654 times 10 to the minus 6, not fitting that on very well here. Now that is going to give us the velocity or the speed. Okay, I would keep the numbers in your scientific calculator. I'm going to shorten things down so they fit on my page here because I'm running out of room. So 206,274 meters per second, that's the velocity. So now I know the velocity. I can come over to the kinetic energy equation. I also know the kinetic energy because, of course, I've got the energy up the top here, which is 2.438 times 10 to the minus 15. That's the kinetic energy, or just the energy. Now, what I want to do is rearrange that equation, and there's a half in there. So I'm going to times both sides by 2. So I'm going to end up with 2ke equals mv squared. I'm then going to move the v squared over by dividing both sides by v squared. So I get 2ke over v squared equals the mass. So we're now going to work out the mass. Remember, at this stage, we're working out the mass of the ion, and that's the same in all of these time of flight equations. You first of all work out the mass of the ion. So we're going to do 2 times 4.38 times 10 to the minus 15. That's the kinetic energy. We're going to divide that by the velocity squared, which is 206,274. And then we want to square that. Don't forget to use brackets in your scientific calculator. The amount of times I'm lazy and forget to put brackets and bracket things, and I end up getting the wrong answer, which is what you do if you're sloppy. Most maths A-level students are well trained on using a scientific calculator, but people doing chemistry who don't do maths, they can sometimes make this mistake. So the answer is 1.145971953. Again, just leave it in your calculator or round that to 1.146 times 10 to the minus 25, and that is our mass. But remember, that's the mass of an ion, and it's the mass of an ion in kilograms. The question asks for the mass in grams, so we need to times by 1,000 to convert to grams. All that does is take away 3 zeros, and so we end up with to the minus 22. Notice here I've rounded to 1.146 times 10 to the minus 22. It's not going to affect your answer. It's so close to 1.146 that is good enough. Now that was for an ion. I want to know for a whole mole. Now a whole mole is made up of 6.022 times 10 to the 23 ions. So I'm timesing it by L, which is 6.022 times 10 to the 23. And that's going to give me the mass in grams of a mole, and the mass in grams of 1 mole is equal to 69.012. Now they asked us for the mass number of germanium, so I need to round that to a whole number, an integer, so it's 69. So the answer here for the full 5 marks, bosh, 69. Guys, really, really important you hit the like. It really, really helps.
If you push the button,
Like me.
Would you like it?
Like. I like it. You're still here? It's over.